Log likelihood. When we calculated the loss for our MNIST example in the preceding chapter, we used this. So this is our loss function from the previous chapter to calculate the loss between the predictions of whether or not something's a 3 or a 7. Just as we moved from sigmoid to softmax, we need to extend the loss function to work with more than just binary classification. It needs to be able to classify any number of categories. In this case, we have 37 categories. Our activations after softmax are between 0 and 1, and sum to 1 for each row in the batch of predictions. Our targets are integers between 0 and 36. In the binary case, we use torch.where to select between inputs and 1 minus inputs. So tensor and then 1 minus all the elements in the tensor. When we treat the binary classification as a general classification problem with two categories, it becomes even easier because, as we saw in the previous section, we now have two columns containing the equivalent of inputs and 1 minus inputs. So all we need to do is select from the appropriate column. Let's try to implement this in PyTorch. For our synthetic 3s and 7s example, let's say these are our labels. Okay, so softmax activations after we had the tensors. Okay, so for each item in targ, we can use that to select the appropriate column of SM softmax activations using tensor indexing like so. Okay, so range of 6. Okay, so take every index 0, 1, 2, 3, whatever. Take now the I guess the target. So we're gonna select most likely, what are we looking at? All of this most likely 1, 2, 3, 2. Oh, I see. Oh, okay. To see what's exactly happening here, let's put all the columns together in a table. Here are the first two columns. Here, the first two columns are our activation. Then we have the targets, the row index, and finally shown in the preceding code. Okay, so this is the tensor. And then what we want to do is for every index, we want to take that target. Okay, so this is complicated. Okay, so the likelihood to get a 3 is 0.6, and then for 7 is 0.3. The loss here is going to be 0.6 because of this here. Okay. Okay, so then if 3 is 0.1 and 7 is 0.8, but the target is 0, then we're going to have to take this one here. So if 3 is 0, or sorry, 3 is 0.99, 0.99, 7 is 0.0033, but the target is 1, is going to be 0.033. Okay, that makes more sense. Okay, so looking at this table, you can see that the final column can be calculated by taking the targ and IDX columns as indices into a two-column matrix containing 3 and 7 columns. Yeah, so that's what it's doing. You're basically for going from 0 to 5, right? From 0 to 5, you're just picking whether, based off of the target, either 0 or 1. You're going to just select that from this table here. So it could be either 0.625, and maybe in another instance is this one, another instance is this one, another instance is this one, based off of what the ground truth is. Okay. So that's what SMX IDX targ is doing. The really interesting thing here is that this works just as well with more than two columns. To see this, consider what would happen if we added an activation column for every digit 0 through 9 and then targ contained a number from 0 to 9. As long as the activation columns sum to 1, as they will if we use softmax, we'll have a loss function that shows how well we're predicting each digit. We're picking the loss only from the column containing the correct label. We don't need to consider the other columns because by the definition of softmax, they add up to 1 minus the activation corresponding to the correct label. Therefore, making the activation for the correct label as high as possible must mean we're also decreasing the activations of the remaining columns. PyTorch provides a function that does exactly the same thing as smx range n targ, except it takes the negative, because when applying the log afterward, we will have negative numbers called the NLL loss, negative log likelihood. So we're going to just take the negative of that, and we're going to get negative 0.6025 and all the negatives of whatever we just saw earlier. Okay, so the equivalent is just this. Okay, so these two, taking the negative of this is the same thing as just calling the PyTorch function NLL loss. Despite its name, this PyTorch function does not take the log. We'll see why in the next section. But first, let's see why taking the logarithm can be useful. Taking the log. The function we saw in the previous section works quite well as a loss function, but we can make it a bit better. The problem is that we are using probabilities, and probabilities cannot be smaller than 0 or greater than 1. This means our model will not care whether it predicts 0.99 or 0.999. Indeed, those numbers are very close together, but in another sense, 0.999 is 10 times more confident than 0.99. So we want to transform our numbers between 0 and 1 to instead be between negative infinity and infinity. There is a mathematical function that does exactly this, the logarithm, available as torch.log. It is not defined for numbers less than 0 and looks like this. Plot function, torch.log, min 0, max 4. Let's see what that looks like. Okay. Does logarithm ring a bell? The logarithm function has this identity. So y goes b to the a. So the goal here is to, okay, so how log works is that you want to find the number that can get you y. So in this case, b to the a, you want to find a based off of how many times do you need to raise, how many times do you need to multiply b to get y? Those many number of times is the answer a. So in this case, we're assuming that log yb returns log y base b. However, PyTorch doesn't define log this way. Log in Python uses the special number e as the base. Perhaps a logarithm is something that you have not thought about for the last 20 years or so, but it's a mathematical idea that is going to be really critical for many things in deep learning. So now would be a great time to refresh your memory. The key thing to know about logarithms is this relationship. So log a times b is the same thing as log of a plus log b. When we see it in that format, it looks a bit boring, but think about what it really means. It means that the logarithms increase linearly when the underlying signal increases exponentially or multiplicatively. This is used, for instance, in the Richter scale of earthquake severity and the dB scale of noise levels. It is also often used on financial charts where we want to show compound growth rates more clearly. Computer scientists love using logarithms because it means that modification, which can create really large and really small numbers, can be replaced by addition, which is much less likely to result in scales that are difficult for our computers to handle. Sylvain says, it's not just computer science who love logs. Until computers came along, engineers and scientists used a special ruler called a slide rule that did multiplication by adding logarithms. Logarithms are widely used in physics for multiplying very big or very small numbers and many other fields. Taking the mean of the positive or negative log of our probabilities, depending on whether it's the correct or incorrect class, gives us the negative log likelihood loss. Okay, taking the mean of the positive or negative log of all our probabilities. In PyTorch, NLL loss assumes that you already took the log of the softmax, so it doesn't do the logarithm for you. Okay, so that's important detail. You're going to run NLL loss. That already assumes that what you're going to be passing in is you've already taken the log of it. That's the result of your log. So That's very confusing indeed. Confusing name beware. The NLL in NLL loss stands for negative log likelihood, but it doesn't actually take the log at all. It assumes you already have taken the log, so all it's going to do is probably just negate it. PyTorch has a function called log softmax that combines log and softmax in a fast and accurate way. NLL loss is designed to be used after the log softmax. So when we first take the softmax and then the log likelihood of that, the combination is called cross entropy loss. Okay, so take the softmax and then the log likelihood. In PyTorch, this is available as nn.cross entropy loss, which in practice does log softmax and then NLL loss. Loss func and n.cross entropy loss. As you see, this is a class. Instantiating it gives you an object that behaves like a function. Okay? All PyTorch loss functions are provided in two forms. The class form just shown as well as a plain functional form available in the F namespace. F.cross entropy is the same thing as this one. Okay? Either one works fine and can be used in any situation. We've noticed that most people tend to use the class version, and that's more often used in PyTorch's official docs and examples, so we'll tend to use that too. By default, PyTorch loss functions take the mean of the loss of all items. Cool. You can use reduction equals none to disable that. So you're not taking the mean anymore, you're just taking the individual. Okay. Sylvan says, an interesting feature about cross entropy loss appears when we consider its gradient. The gradient of cross entropy AB is softmax A minus B. Since softmax A is the final activation of the model, that means that the gradient is proportional to the difference between the prediction and the target. The gradient is proportional to the difference between the prediction and the target. Oh yeah, that's true. Okay, this is the same as the mean squared error in regression, assuming there's no final activation function such as that added by the y range. Since the gradient of a minus b squared is 2a minus b, because the gradient is linear, we won't see sudden jumps or exponential increases in gradients, which should lead to a smoother training of models. So we now have seen all the places hidden behind our loss function, but while this puts a number on how well or badly our model is doing, it does nothing to help us know if it's any good. Let's now see some ways to interpret our model's predictions. Model interpretation. It's very hard to interpret loss functions directly because they are designed to be things computers can differentiate and optimize, not things that people can understand. That's why we have metrics. These are not used in the optimization process, but just to help us poor humans understand what's going on. In this case, our accuracy is looking pretty good already. So where are we making mistakes? So we saw in chapter 1 that we can use a confusion matrix to see where our model is doing well and where it's doing badly. Okay, I think let's just do classification interpretation from learner, and then we're going to plot the confusion matrix. I think it's going to be a big one. Okay, what does it even mean? I see. Let's see, like we have like one misprediction of Sphinx. Thought it was like a Chihuahua, or yeah, no, it thought we have a Chihuahua, but it thought it was a Sphinx. There we go. So we have the actual, and then we have the predicted here. Okay. Oh dear, in this case, a confusion matrix is very hard to read. We have 37 pet breeds, which means that we have 37 by 37 entries in this giant matrix. Instead, we can use the most confused method, which just shows us the cells of the confusion matrix with the most incorrect predictions, here with at least 5 or more. So this is another helper. Let's see. Interp.most confused min val. So I'm taking the min value of the occurrences, I think. So let's just finding all that stuff. It's probably just inferencing. Okay, yeah, Ragdoll Berman. You had 8 of them, I guess. American Pit Bull Terrier, Staffordshire. Okay, cool. Since we are not pet breed experts, it's hard for us to know whether these category errors reflect actual difficulties in recognizing breeds. So again, we turn to Google. A little bit of Googling tells us that the most common category errors shown here are breed differences that even expert breeders sometimes disagree with or disagree about. So this gives us some comfort that we are on the right track. Okay. We seem to have a good baseline. What can we do now to make it even better? Improving our model. We will now look at a range of techniques to improve the training of our model and make it better. Ooh, how exciting. While doing so, we will explain a little bit more about transfer learning and how to fine-tune our pre-trained model as best as possible without breaking the pre-trained weights. The first thing we need to set when training a model is the learning rate. We saw in the previous chapter that it needs to be just right to train as efficiently as possible. So how do we pick a good one? FastAI provides a tool for this. The learning rate finder. One of the most important things we can do when training a model is to make sure that we have the right learning rate. If our learning rate is too low, it can take many epochs to train our model. Not only does this waste time, but it also means that we may have problems with overfitting, because every time we do a complete pass through the data, we give our model a chance to memorize it. So let's just make our learning rate really high, right? Sure, let's try that and see what happens. Let's do that. So learning rate is going to be 0.1, and that is considered pretty high. So let's fine tune with one epoch with 0.1 as our learning rate. Where do we end up? Let's see here. It's going to eval. So, okay, it looks okay, but I'm guessing it's going to step too far. Well, actually, that's not even that accurate, because it's not even like less than 1 in this case. Okay, so it looks like for our case, we had a pretty high training and validation loss too, same like him. I consider this to be pretty high, to be honest. And the error rate's pretty high too. Oops, where are we? That doesn't look good. Here's what happened. The optimizer stepped in the correct direction, but it stepped so far that it totally overshot the minimum loss. Repeating that multiple times makes it go further and further away, not closer and closer. What do we do to find the perfect learning rate? Not too high and not too low. In 2015, researcher Leslie Smith came up with a brilliant idea called the learning rate finder. His idea was to start with a very small learning rate, something so small that we would never expect it to be too big to handle. We use that for one mini batch, find out what the losses are afterwards, and then increase the learning rate by a certain percentage, doubling it each time. Then we do another mini batch, track the loss, and double the learning rate again. We keep doing this until the loss gets worse instead of better. This is the point where we know we have gone too far. We then select the learning rate a bit lower than this point. Our advice is either pick either of these. One order of magnitude less than where the minimum loss was achieved. Basically divide the minimum divided by 10. The last point where the loss was clearly decreasing. Okay. The learning rate finder computes those points on the curve to help you. Both these rules usually give around the same value. In the first chapter, we didn't specify learning rate using the default value from the FastAI library, which is 1. Okay, 1 times 10 to negative 3 is a default. Okay, so we can use this. So let's find our learning rate, our optimal learning rate. So it's learn equals CNN, learner, DLs, ResNet 34, metrics, error rate, and then LR min, LR steep, learn.lr fine, based off of our data set. Okay, so it's gonna do. Is it really going to run through the whole thing again? Let's see. I think so. Okay. So it's gonna find probably the minimum is 8 times 10 to negative 3. Okay. Not enough values to unpack. Why? Expected to got 1. LR fine. Not sure why, but it looks like we are okay. Oh, I forgot to print this. Let's print this here. But it got an error here, so let's see what happens. Not enough values to unpack. Why? I don't know. It looks like the valley happened here, which is 10, where it starts to negative 3 with, like he said. So, so we can see on this plot that in the range of 1 times 10 to the negative 6 to 1 times 10 to the negative 3, nothing really happens and the model doesn't train. Then the loss starts to decrease until it reaches a minimum and then increases again. We don't want a learning rate greater than 1 times 10 to negative 1, as it will cause training to diverge. You can try for yourself. But 1 times 10 to negative 1 is already too high. At this stage, we've left the period where the loss was decreasing steadily. In this learning rate plot, it appears that the learning rate around 3e negative 3, so 3 times 10 to negative 3, would be appropriate. So let's choose that. So let's fine tune over that. So yeah, see, we want the training loss and validation loss to be very like close to each other, but also like under under 1 in this case, because the error rate is then very low. And we're only fine tuning for 2 epochs too, so we passed through the data set just twice. Okay, so we also got a very good error rate, and training loss and validation loss are really good. Logarithmic scale. The learning rate finder plot has a logarithmic scale, which is why the middle point between 1e negative 3 and 1e negative 2 is between 3e negative 3 and 4e negative 3. This is because we care mostly about the order of magnitude of the learning rate. It's interesting that the learning rate finder was discovered only in 2015, while neural networks have been under development since the 1950s. Throughout that time, finding a good learning rate has been perhaps the most important and challenging issue for practitioners. The solution does not require any advanced math, giant computing resources, or huge datasets, or anything else that would make it inaccessible to any curious researcher. Furthermore, Smith was not part of some exclusive Silicon Valley lab, but was working as a naval researcher. All of this is to say, breakthrough work in deep learning absolutely does not require access to vast resources, elite teams, or advanced mathematical ideas. Lots of work remains to be done that requires just a bit of common sense, creativity, and tenacity. Now that we have a good learning rate to train our model, let's look at how we can fine-tune the weights of a pre-trained model. Unfreezing and transfer learning. We discussed briefly in Chapter 1 how transfer learning works. We saw that the basic idea that a pre-trained model, trained potentially on millions of data points such as ImageNet, is fine-tuned for another task. But what does this really mean? We now know that a convolutional neural network consists of many linear layers with a nonlinear activation function between each pair, followed by one or more final linear layers with an activation function such as softmax at the very end. The final linear layer uses a matrix with enough columns such that the output size is the same as the number of classes in our model, assuming we are doing classification. This final linear layer is unlikely to be of any use for us when we are fine-tuning in a transfer learning setting, because it is specifically designed to classify the categories in the original pre-training dataset. So when we do transfer learning, we remove it, throw it away, and replace it with a new linear layer with the correct number of outputs for our desired task. In this case, there will be 37 activations. This newly added linear layer will have entirely random weights. Therefore, our model prior to fine-tuning has entirely random outputs. But that does not mean that it is an entirely random model. All the layers prior to the last one have been carefully trained to be good at image classification tasks in general. As we saw in the images from Zeiler and Fergus' paper in Chapter 1, figures 1-10 through 1-13, the first few layers encode general concepts such as finding gradients and edges, and later layers encode concepts that are still useful for us, such as finding eyeballs and fur. We want to train a model in such a way that we allow it to remember all of these generally useful ideas from the pre-trained model, use them to solve our particular class, like classifying pet breeds, and adjust them only as required for the specifics of our particular task. Our challenge when fine-tuning is to replace the random weights in our added linear layers with weights that correctly achieve our desired task, such as classifying pet breeds, without breaking the carefully pre-trained weights and other layers. That's always the hard thing with fine-tuning, is that you can wreck your existing model. Catastrophic forgetting, that is. A simple trick can allow us this to happen. Tell the optimizer to update the weights in only those randomly added final layers, so you freeze the earlier layers of the model. Don't change the weights in the rest of the neural network at all. This is called freezing those pre-trained layers. When we create a model from a pre-trained network, fastai automatically freezes all of the pre-trained layers for us. When we call the fine-tune method, fastai does two things. It trains the randomly added layers for one epoch with all other layers frozen, unfreezes all the layers, and trains them for the number of epochs requested. So trains randomly the added layers for one epoch with all other layers frozen, then unfreezes all the layers and trains them for the number of epochs requested. It does two things. So it still trains all the layers after one epoch. Okay. Oh, that's what this is for. I see. Okay. That's okay. So this is the layers that is added, and this is like all the other layers later. Okay. So although this is a reasonable default approach, it is likely that for your particular data set, you may get better results by doing things slightly differently. The fine-tune method has parameters you can use to change its behavior, but it might be easiest for you to just call the underlying methods directly if you want to get custom behavior. Remember that you can see the source code for the method by using the following syntax. Learn.finetune ? Let's try doing this manually ourselves. First of all, we will train the randomly added layers for 3 epochs using fit1cycle, as mentioned in Chapter 1. Fit1cycle is a suggested way to train models without using fine-tune. We'll see why later in the book. In short, what fit1cycle does is start training at a low learning rate, gradually increasing it for the first section of training, and then gradually decreasing it again for the last section of training. So what we can do is do learn equals CNN learner DLs resnet 34 resent resnet 34 metrics error rate, and then we could do learn.fit1cycle for 3 epochs at 3e-3 learning rate. And let's see what else we do. So this will just train the last layers, or the very last layer. And so by default, the model, the pre-trained model, it has all its layers frozen. So only training one of these layers in this case. Oh, and that's why this is usually faster. Okay, makes sense. Okay, it's going to eval. Cool. Okay. So after that, we actually do a learning rate finder. Oh, after unfreezing, I see. So now it's even less because it turns out by that point your model is actually smart for the task. Okay, that makes sense because generally the smarter your model is already, you don't want to disturb the model's abilities, so you just like tune very, very slightly. So we'll unfreeze the model and then run LR find again, because having more layers to train and weights have already been trained for 3 epochs means our previously found learning rate isn't appropriate anymore. I see. So LR.find. Okay, so note that the graph is a little different from when we had random weights. We don't have that sharp descent that indicates that the model is training. That's because our model has been trained already. Here we have a somewhat flat area before a sharp increase. And that we should take a point well before that sharp increase, for instance, when E negative 5. The point with the max, oh, so this is when it starts to like go backwards and get worse. It'll train your model to be worse. So here we are. So what we want to do is we're going to unfreeze, learn.unfreeze. So we're going to unfreeze the earlier layers in the model, and then learn.lr find. Okay. And it's going to go through, I guess, one batch or one epoch. Okay. So, and then we can go for 6 epochs with a learning rate of 1e to negative 5, because that's where we found that this is like at the deepest point. Okay, so suggested learning rate is actually 275 times 10 to negative 6. Okay, let's do it. Learn.fit one cycle, because we've already unfrozen everything. Going to 6 epochs. LR max is going to be, what is it? 2.75 E negative 6. Okay. 6 epochs, that's quite a lot, but let's do it. It looks like he got really good results here, though. Like at this point, you have like literally very low error rate, 5% of the time, I guess. This has improved our model a bit, but there's more we can do. The deepest layers of our pre-trained model might not need as high a learning rate as the last one, so we should probably use different learning rates for those. This is known as discriminative learning rates. Okay, let's read that after we finish training this, so I'll come back to it. Okay, so we basically got around the same result as the book, so good stuff. Discriminative learning rates. Even after we unfreeze, we still care a lot about the quality of those pre-trained weights. We would not expect that the best learning rate for those pre-trained parameters would be as high for the randomly added parameters, even after we have tuned those randomly added parameters for a few epochs. Remember, the pre-trained weights have been trained for hundreds of epochs on millions of images. In addition, do you remember the images that we saw in chapter 1 showing what each layer learns? The first layer learns very simple foundations like edge and gradient detectors. These are likely to just be as useful for nearly any task. The later layers learn a much more complex concepts like eye and sunset, which might not be useful in your task at all. Maybe you're classifying car models, for instance. So it makes sense that to let the later layers fine-tune more quickly than earlier layers. Therefore, FastAI's default approach is to use discriminative learning rates. This technique was originally developed in the OMFIT approach to NLP transfer learning that we will introduce in Chapter 10. Like many good ideas in deep learning, it is extremely simple. Use a lower learning rate for the early layers of the neural network and a higher learning rate for the later layers, and especially in the randomly added layers. The idea is based on the insights developed by Jason Yosinki et al., who showed in 2014 that with transfer learning, different layers of a neural network should train at different speeds, as seen in Figure 5-4. So yeah, okay, that makes sense. Like different layers learn at different rates. You should probably have a different learning rate for every specific layer. So FastAI lets you pass a Python slice object anywhere that a learning rate is expected. The first value passed will be the learning rate in the earliest layer of the neural network, and the second value will be the learning rate in the final layer. The layers in between will have learning rates that are multiplicatively multiplicatively equidistant throughout that range. Let's use this approach to replicate the previous training, but this time we'll set only the lowest layer of our net to a learning rate of 1e negative 6. The other layers will scale up to 1e negative 4. Let's train for a while and see what happens. Okay, so we're going to restart the training from the beginning, and this time we're going to use a slice object, and it's going to interpolate the learning rate values. So it's going to like slice them up and then apply a specific learning rate to all the other layers. So again, I'll come back to this. Okay, it looks like we're done with our 15 epics. We did get our error rate to the lowest ever, so that's great. And look at the train and validation, they are like in sync. That is really good. So now the fine-tuning is working great. Fast AI can show us a graph of the training and validation loss. Okay, so learn.recorder.plot loss. Let's see how ours look like. Awesome. As you can see, the training loss keeps getting better and better, but notice that even the validation loss improvement slows and sometimes gets worse. This is the point at which the model is starting to overfit. In particular, the model is becoming overconfident of its predictions, but this does not mean it's getting less accurate necessarily. Take a look at the table of training results per epoch, and you will often see that the accuracy continues improving, even as the validation loss gets worse. In the end, what matters is your accuracy, or more generally, your chosen metrics, not the loss. The loss is just a function we've given the computer to help us optimize. Another decision you have to make when training the model is how long to train for, and we'll consider that next. Alright, let's do that next time. Selecting the number of epochs. Often, you will find that you are limited by time rather than generalization and accuracy when choosing how many epochs to train for. So, your first approach to training should be simply pick a number of epochs that will train in the amount of time that you are happy to wait for. Then, look at the training and validation loss plots as shown previously, and in particular your metrics. If you see that they are still getting better even in your final epochs, you know that you have not trained for too long. On the other hand, you may well see that the metrics you have chosen are really getting worse at the end of training. Remember, it's not that we're looking for the validation loss to get worse, but the actual metrics. Your validation loss will first get worse during training because the model gets overconfident, and only later will get worse because it is incorrectly memorizing the data. We care in practice about only the latter issue. Remember, our loss function is something that we use to allow our optimizer to have something it can differentiate and optimize. It's not the thing we care about in practice. Before the days of, I think it's one cycle? Before the days of one cycle training, it was common to save the model at the end of each epoch, and then select whichever model had the best accuracy out of all the models saved in each epoch. This is known as early stopping. However, this is unlikely to give you the best answer, because those epochs in the middle occur before the learning rate has had a chance to reach the small values, where it can really find the best result. Therefore, if you find that you have overfit, what you should do is retrain your model from scratch. And this time, select a total number of epochs based on where your previous best results were found. If you have time to train for more epochs, you may want to instead use that time to train more parameters. That is, use a deeper architecture. Deeper architectures. In general, a model with more parameters can model your data more accurately. There are lots and lots of caveats to this generalization, and it depends on the specifics of the architectures you are using, but it is a reasonable rule of thumb for now. For most of the architectures that we will be seeing in this book, you can create larger versions of them by simply adding more layers. However, since we want to use pre-trained models, we need to make sure that we choose a number of layers that have already been pre-trained for us. This is why in practice, architectures tend to come in a small number of variants. For instance, the ResNet architecture that we are using in this chapter comes in variants with 18, 34, 50, 101, and 152 layers, pre-trained on ImageNet. A larger, more layers and parameters, sometimes described as the capacity of a model. So the larger version of a ResNet will always be able to give us a better training loss, but it can suffer more from overfitting because it has more parameters to overfit with. In general, a bigger model has the ability to capture the real underlying relationships in your data, as well as to capture and memorize the specific details of your individual images. However, using a deeper model is going to require more GPU RAM, so you may need to lower the size of your batches to avoid an out-of-memory error. This happens when you try to fit too much inside your GPU and it looks like this. CUDA runtime error, out of memory. We get this a lot. You may have to restart your notebook when this happens. The way to solve it is to use a smaller batch size, which means passing smaller groups of images at any given time through your model. You can pass the batch size you want to call by creating your data loaders with BS equals. So to avoid out of memory errors, the easiest way to kind of mitigate that is to use smaller batch sizes. Okay, and you can specify that by creating data loaders with, so you have to create a data loader already with a predefined batch size, and this is something I had trouble with before. So the other downside of deeper architectures is that they take quite a bit longer to train. One technique that can speed things up a lot is mixed precision training. This refers to using less precise numbers, half precision floating point, or also called FP16, where possible during training. As we are writing these words in early 2020, nearly all current NVIDIA GPUs support a special feature called Tensor Core that can dramatically speed up neural network training by 2 to 3 times. They also require a lot less GPU memory. To enable this feature in FastAI, just add to FP16 after your learner creation. You will also need to import the module. You can't really know the best architecture for your particular problem ahead of time. You need to try training some. So let's try ResNet 50 now with mixed precision. Okay, let's do it. From FastAI to, oh wait, we don't have that. Callback, FP16, import, start, learn equals CNN learner, DLs, ResNet 50, metrics, error rate, dot to FP16. Okay, so let's see, learn.fine-tune, and this should be much faster, I expect, because we are on a 5070 here, and 5070s did not exist back then, so okay, so freeze epochs. I don't know what that means, but let's go. Okay, let's see, it should be much faster. Oh, I think it is, because last time it was like 40 something seconds to finish. Now it's only like 20, and this thing is working quite fast too. Yeah, I still don't understand how this is only 30 watts, but it's okay. I feel like I'm losing a lot of performance. Okay, so that's cool. Okay, 32 seconds. So, and I think it'll only get faster and faster because the first one is it's like kind of like a pre-run to find things. Okay, let's just keep going. So yeah, this person Jeremy's computer only took about 20 seconds. Okay, so you'll see here we've gone back to using fine-tune since it's so handy. We can pass freeze epochs to tell fastai how many epochs to train for while frozen. It will automatically change learning rates appropriately for most data sets. In this case, we're not seeing a clear win from the deeper model. This is useful to remember. So what he's saying is that the losses don't get that much better. So the validation loss stops to decrease significantly while the train loss keeps decreasing. And this is actually due to like a bigger model, ResNet 50, and it just starts to have signs of overfitting to the training data. So bigger models aren't necessarily better models for your particular case. Make sure you try small models before you start scaling up. Conclusion. In this chapter, you learned some important practical tips, both for getting your image data ready for modeling, presizing data block summary, and for fitting the model, learning rate finder, unfreezing discriminative learning rates, setting the number of epochs, and using deeper architectures. Using these tools will help you build more accurate image models more quickly. We also discussed cross-entropy loss. This part of the book is worth spending plenty of time on. You aren't likely to need to implement cross-entropy loss from scratch yourself in practice, but it's important you understand the inputs to and output from that function, because it, or a variant of it, as we'll see in the next chapter, is used in nearly every classification model. So when you want to debug a model or put a model in production or improve the accuracy of a model, you're going to need to be able to look at its activations and loss and understand what's going on and why. You can't do that properly if you don't understand your loss function. If cross-entropy loss hasn't clicked for you just yet, don't worry, you'll get there. First, go back to the preceding chapter and make sure you really understand MNIST loss. Then work gradually through the cells of the notebook for this chapter, where we step through each piece of cross-entropy loss. Make sure you understand what part or what each calculation is doing and why. Try creating some small tensors yourself and pass them into the functions to see what they return. Remember, the choices made in the implementation of cross-entropy are not the only possible choices that could have been made. Just as when we looked at the regression, we could choose between mean squared error and mean absolute difference. We could change the details here too. If you have other ideas for possible functions that you think might work, feel free to give them a try in this chapter's notebook. Fair warning though, you probably find that the model will be slower to train and less accurate. That's because the gradient of cross-entropy loss is proportional to the difference of the activation and the target. So SGD always gets a nicely scaled step for the weights. Okay, questionnaire. Maybe. Okay, let's continue on. Chapter 6. Other computer vision problems. In the previous chapter, you learned some important practical techniques for training models in practice. Considerations like selecting learning rates and the number of epochs are very important to getting good results. In this chapter, we are going to look at two other types of computer vision problems: multi-label classification and regression. The first one occurs when you want to predict more than one label per image, or sometimes none at all. And the second occurs when your labels are one or several numbers, a quantity instead of a category. In the process, we will study more deeply the output activations, targets, and loss functions in deep learning models. Multi-label classification. Multi-label classification refers to the problem of identifying the categories of objects in images that may not contain exactly one type of object. There may be more than one kind of object, or there may be no objects at all in the classes you are looking for. For instance, this would have been a great approach for our bear classifier. One problem with the bear classifier that we rolled out in chapter 2 was that if a user uploaded something that wasn't any kind of bear, the model would still say it was either a grizzly, black, or teddy bear. It had no ability to predict not a bear at all. In fact, after we have completed this chapter, it would be a great exercise for you to go back to your image classifier application and try to retrain it using the multi-label technique, and then test it by passing in an image that is not of any of your recognized classes. In practice, we have not seen many examples of people training multi-label classifiers for this purpose, but we often see both users and developers complaining about this problem. It appears that this simple solution is not at all widely understood or appreciated, because in practice it is probably more common to have some images with 0 matches or more than 1 match. We should probably expect in practice that multi-label classifiers are more widely applicable than single label classifiers. So, first, let's see what a multi-label dataset looks like. Then we'll explain how to get it ready for our model. You'll see that the architecture of the model does not change from the preceding chapter, only the loss function does. So let's start with the data. The data. For our example, we are going to use the Pascal dataset, which can have more than one kind of classified object per image. Okay, so now it's time to create a new notebook. Okay, so get status, just add the chapter, and then git push. Okay, now it's time to create the new book chapter 06 book.ipynb, and then let's select the kernel, and then I guess we have to import stuff always, right? So just import that. Since we're still working with vision related tasks. Oops. Okay, so looks like we're okay. It's just probably, yeah, it's probably running still. I would like a nice animation, but okay. Okay. So we begin by downloading and extracting the dataset per usual. So path equals untar data urls.pascal 2007. So we run this one. We're still on pending for all of these. Let's just restart the kernel. Boom. Okay. Let's run it again. There we go. That looks like it's doing something. Okay. Now it's download. Looks like a big data set. Oh yeah, that is. Okay. So let's continue reading. Okay. This data set is different from the ones we have seen before in that it is not structured by file name and folder, but instead comes with a CSV file telling us what labels to use for each image. We can inspect the CSV file by reading it into a pandas data frame. df equals pd read CSV. Okay, handy tool. So let's create a data frame. I don't really know what that is, but okay. Let's see, df. My spacebar is kind of messed up again. Or actually, I think in general this thing is okay. This notebook is really messed up. Okay, so let's just do that. Yeah, spacebar doesn't work. Okay, how are we gonna solve this? My laptop keyboard is not working with this. I'm betting that it is just anti-gravity. So let's close that. Okay, so anti-gravity gave me a freaking hard time, so I'm just going to use cursor. Okay, yeah, so let's create that data frame. Yay, spacebar works. pd.read CSV path train.csv, and then df.head to show what's the first few items. So we have file name, we have the labels to it. So this is multi-label, right? So this picture probably contains a horse and a person. Is valid, is probably validation data. Yeah, so as you can see, the list of categories in each image is shown as a space delimited string. Pandas and data frames. No, it's not actually a panda. Pandas is a Python library that is used to manipulate and analyze tabular and time series data. The main class is data frame, which represents a table of rows and columns. You can get a data frame from a CSV file, a database table, Python dictionaries, and many other sources. In Jupyter, a data frame is output as a formatted table as shown here. You can access rows and columns of a data frame with the iloc property. So access rows and columns, iloc, okay, as if it was a matrix. So to get the first column, you're going to just, okay, I guess colon and then 0. Sure. And then get the first row, I would assume, is going to be 0 colon. Okay, so trailing colons are always optional. All right. So that'll get us, okay, like a table of the first row, I see. So each row is the property, and then each column will tell us the value. So you can grab a column by name and by indexing it into the data frame directly. So just grab all the file name column values, and then you can create new columns and do calculations using columns. Okay. Okay, so you create a new data frame and you just like add dynamically. Cool. Oh, interesting. That's cool. Pandas is a fast and flexible library and an important part of every data scientist's Python toolbox. Unfortunately, its API can be rather confusing and surprising, so it takes a while to get familiar with. If you haven't used pandas before, we suggest going through the tutorial. We are particularly fond of Python for data analysis by O'Reilly by Wes McKinney, the creator of pandas. It also covers other important libraries like matplotlib and numpy. We also try to briefly describe pandas functionality, and we will try to briefly describe pandas functionality we use as we come across it, but will not go into the level of detail of McKinney's book. So now that we have seen what the data looks like, let's make it ready for model training. Constructing a data block. How do we convert from a data frame object to a data loaders object? We generally suggest using the data block API for creating a data loaders object, where possible, since it provides a good mix of flexibility and simplicity. Here we will show you the steps that we take to use the data block API to construct a data loaders object in practice using this dataset as an example. So we will learn how to use the data block API to build data loaders. As we have seen, PyTorch and fastai have two main classes for representing and accessing a training set or validation set. Dataset, which is a collection that returns a tuple of your independent and dependent variable for a single item. Okay, and then a data loader, an iterator that provides a stream of mini batches where each mini batch is a couple of a batch of independent variables and batch dependent variables. Okay, so it's kind of like a group of examples. So data loader gives you a group of the examples. On top of these, fastai provides two classes for bringing your training and validation sets together. So datasets, dataset and datasets. Datasets is an iterator that contains a training dataset and a validation dataset. Data loaders, an object that contains a training data loader and a validation data loader. Since a data loader builds on top of a dataset and adds additional functionality to it, collating multiple items into a mini batch, It's often easiest to start by creating and testing data sets and then looking at data loaders after that's working. When we create a data block, we build up gradually, step by step, and use the notebook to check our data along the way. This is a great way to make sure that you maintain momentum as you are coding, and that you keep an eye for any problems. It's easy to debug because you know that if a problem arises, it is the line of the code that you just typed. Let's start with the simple case, which is a data block created with no parameters. So simple dblock, data block. Dblock is equal to data block, boom, empty data block. We can create a datasets object from this. So data frame. Whoa. Okay, so the only thing needed is a source. In this case, our data frame. Oh yeah, this one here. Okay, so data sets is from this pandas data frame. Sure. Dsets, dblock. So data block, data sets. So we're gonna create a data set off from a data block object using our data frame. Wow. Dsets.train 0. Cool. That's like the first example. So this contains a train and a valid data set which we can index into. As you can see, this simply returns a row of the data frame twice. This is because by default, the data block assumes we have two things, input and target. We are going to need to grab the appropriate fields from the data frame, which we can do by passing getX and getY function. Okay, so getX and getY. Dsets train. Well, I'm already there. Oh, we had to modify this. So dblock. Let's just do it here. dblock is going to be data block. GetX is going to be the function that we need to provide. So let's just make a new line here. GetX is a lambda. Lambda R. Take the first name or file name. File name, and then we're going to define getY, and then that'll be the labels. Lambda R labels. And then what we want to do is create a data set off of this data block. Dsets is dblock.datasets using the data frame data. And then let's access the first element in the training data. Okay, so we got cow. I think that's like random. Okay, yeah, it is random. Okay, oops. As you can see, rather than defining a function in the usual way, we are using Python's lambda keyword. This is just a shortcut for defining and then referring to a function. The following more verbose approach is identical. So this is the same thing. Okay, lambda functions are great for quickly iterating, but they are not compatible with serialization. So we advise you to use the more verbose approach if you want to export your learner after training. Lambdas are fine if you're just experimenting. Okay, so that's important to remember. Yeah, lambdas do not serialize. So if we're gonna like take an image of our learner, save it into a pickle or whatever, I think we had to use the more verbose way. And the more verbose way is to just define the functions rather than using lambda. Okay, so we can see that the independent variable will need to be converted into a complete path so that we can open it as an image, and the dependent variable will need to be split on the space character, which is a default for Python split function. So that becomes a list. Okay, looks like we had to go do it the traditional way anyway. Okay, let's do it. So def get x given r, let's do it in a new line, return path train r f name, so that's the file name for that particular row. Then def get y r return r labels dot split. So all the labels available for that specific example, remember they're space delimited, they're just categories, so multi-labeling. Okay, D block is data block with get X as the input to get X, and then get Y as input to get Y. Finally, we had D sets equals D block dot data sets DF. So add the data frame data to the data sets, and then D sets dot train 0 should be much smaller and cleaner. Oops. Wait. Oh wait, this is a single label. We should have the multi-label right here. Sofa, chair, person. Cool. Okay. So to actually open the image and do the conversion to tensors, we will need to use a set of transformations. Block types will provide us with those. We can use the same block types that we have used previously, with one exception. The image block will work fine again because we have a path that points to a valid image, but the category block is not going to work. The problem is that the block returns a single integer, but we need to be able to have multiple labels for each item. To solve this, we use a multi-category block. This type of block expects to receive a list of things, as we have in this case, so let's test it out. Okay, we're going to create data block without the default data block. So default data block was like this, but we don't need it like that anymore. We want to create a multi-category block with the image. And then get X is going to be defined as get X. Get Y is going to be get Y. And then let's create. So then we've already specified X to be the file name, and then Y to be the labels. Okay. So now D sets is equals to D block dot data sets DF. Like stick in the data frame there, and then let's access D sets dot train 0. Okay, cool. So multi-category, I think it's like the one hot encoding stuff. Yep, zeros or ones. So as you can see, our list of categories is not encoded in the same way as it was for the regular category block. In this case, we had a single integer representing which category was present based on its location in our vocab. In this case, however, we instead have a list of ones with a 1 in any position where that category is present. For example, if there is a 1 in the second and fourth positions, that means vocab items 2 and 4 are present in the image. This is known as one-hot encoding. The reason we can't easily just use a list of category indices is that each list would be a different length, and PyTorch requires tensors where everything has to be the same length. Okay, so jargon, one-hot encoding. Using a vector of zeros with 1 in each location that is represented in the data, we encode a list of integers. Okay. I'm just going to stop here for now. Got stuff to do, so yeah. Thanks. So let's check what the categories represent for this example. We are using the convenient torch.where function, which tells us all the indices where our condition is true or false. So we'll type this code here. ID x's is going to be torch.where dsets.train 0 1 equals 1 dot. So we're going to check for anything that equals to 1, and then take the first result, dsets.train.vocab ID x's. So we'll have chair, sofa, TV monitor. So those are the labels for the, I guess, the first element. So with NumPy arrays, PyTorch tensors, and FastAI's L class, we can index directly using a list or vector, which makes a lot of code, such as this example, much clearer and more concise. We have ignored the column is valid up until now, which means that data block has been using a random split by default. To explicitly choose the elements of our validation set, we need to write a function and pass it to splitter, or use one of FastAI's predefined functions or classes. It will take the items, here our whole data frame, and must return 2 or more lists of integers. So this is the implementation of a typical splitter. We're going to take a data frame, and I guess we're going to convert anything that isn't listed as is valid, not is valid, to list. Validation set will be anything that is valid, turn that to list, return both of them, and I guess that's all there is to it. Okay, we can just implement that. Def splitter df, we'll have train, that's going to be df.index. Not df is valid, so that's a bitwise not to list. Then we'll have valid df.index, df is valid to list. Then we'll just return train valid. Okay, and dblock data block blocks is going to be the image block, and then a multi-category block as labels. We're going to define splitter to be the function that we just created. Get x is going to be get x, and then get y is going to be get y. Oops. Okay. Then we should probably write it like this. Okay, and then dsets. It's gonna be dblock.datasets df dsets.train at 0. Oops, missed this. There you go. Looks like there's a specific category coming up here. All right. Let's see here. So as we have discussed, a data loader collates the items from a data set into a mini batch. This is a tuple of tensors, where each tensor simply stacks the items from that location in the dataset item. Now that we have confirmed that the individual items look okay, there's one more step. We need to ensure that we can create our data loaders, which is to ensure that every item is of the same size. To do this, we can use random resize crop. Okay, so random resize crop is going to ensure that all our images are the same size, just like before. Cool. So dblock is going to be data block. Again, blocks is going to be image block class, multi-category block class, and then we are going to provide the splitter implementation. We're going to provide getX. We're also going to provide getY, and then the item transforms. So item transformations, TFMS, random resized crop 128, min scale 0.35. Oops, 0.35. Okay, so let's make that neater again. So blocks, splitter, get X, get Y, and the item transforms, and end it right there. DLs, data loaders, it's going to be data block.data loaders with the data frame passed in. Okay. I don't know what that is, but okay. DLs. What happened here? Oh. Okay, there we go. DLs.show batch. N rows 1, and calls equals 3. Cool. So we have train, bicycle, and car with person Okay. That makes sense. This one has two labels associated with it. Okay, so remember that if anything goes wrong when you create your data loaders from your data block, or if you want to view exactly what happens with your data block, you can use the summary method we presented in the previous chapter. Our data is now ready for training a model. As we will see, nothing is going to change when we create our learner, but behind the scenes, the fastai library will pick a new loss function for us: binary cross entropy. Now we'll create our learner. We saw in chapter 4 that a learner object contains four main things: the model, a data loader's object, and an optimizer, and the loss function to use. We already have our data loaders. We can leverage FastAI's resonant models, which we'll learn how to create from scratch later, and we know how to create an SGD optimizer. So let's focus on ensuring we have a suitable loss function. To do this, let's use CNN Learner to create a learner so we can look at its activations. Okay. Learn CNN Learner DLs ResNet 18. Cool. So we downloaded the ResNet 18 model, about 44.7 meg. We also saw that the model in learner is generally an object of a class inheriting from nn.module, and that we can call it using parentheses, and it will return the activations of a model. You should pass it to your independent variable as a mini batch. We can try it out by grabbing a mini batch from our data loader and passing it to the model. Okay, makes sense? XY is going to be dls.train dot one batch. So in the training set, get one batch. Activations or actives is going to be learn.model given x actives.shape. Okay, so we have 6420. So batch of 64 items, and I think 20 like each item has like possible 20 categories to be in. So think about why actives has this shape. We have a batch size of 64 and we need to calculate the probability of each of 20 categories. Yep. Here's what one of those activations look like. Okay, so let's look at one of those. Actives 0. All right. So a bunch of floating points. I think this is maybe I guess it's probability, or not really, not probability yet. Just like basically a result of one of the layers. So getting model activations. Knowing how to manually get a mini batch and pass it to a model and look at the activations and losses is really important for debugging your model. It is also very helpful for learning so that you can exactly see what's going on. They aren't scaled to between 0 and 1, but we learned how to do that in chapter 4 using the sigmoid function. We also saw how to calculate a loss based on this. This is our loss function from chapter 4 with the addition of log as discussed in the preceding chapter. Okay, so let's write this loss function. Def binary cross entropy inputs targets. Okay, so inputs is going to be inputs.sigmoid, and then return negative torch.where. So negative, what's it? Negative log prob. Where? Oops. Dot where targets is going to equal to 1. Inputs 1 minus inputs. Dot log dot mean. Okay. So note that because we have a one hot code encoded dependent variable, we can't directly use NLL loss or softmax, and therefore we can't use cross entropy. Softmax, as we saw, requires that all predictions sum to 1 and tends to push one activation to be much larger than the others because of the use of the exponential. However, we may well have multiple objects that we're confident appear in the image. So restricting the maximum sum of activations to 1 is not a good idea. By the same reasoning, we may want the sum to be less than 1 if we don't think any of the categories appear in an image. Okay. NL loss, as we saw, returns the value of just one activation, the single activation corresponding with the single label for an item. This doesn't make sense when we have multiple labels. Okay. So NL loss is just for the regular one category per input. So on the other hand, the binary cross entropy function, which is just ms lost along with log, provides what we need thanks to the magic of PyTorch's element-wise operations. Each activation will be compared to each target for each column, so we don't have to do anything to make this function work for multiple columns. Okay. Jeremy says, one of the things I really like about working with libraries like PyTorch with broadcasting and element-wise operations is that quite frequently I find I can write code that works equally well for a single item or a batch of items without changes. Binary cross entropy is a great example of this. By using these operations, we don't have to write loops ourselves and can rely on PyTorch to do the looping we need as appropriate for the rank of the protensors we're working with. PyTorch already provides this function for us. In fact, it provides a number of versions with rather confusing names. f.binary cross entropy and its module equivalent nn.bce loss calculate cross entropy on a one hot encoded target, but do not include the initial sigmoid. Normally, for one hot encoded targets, you'll want f.binary, which do both sigmoid and binary cross entropy in a single function, as in the preceding example. The equivalent for single label datasets like MNIST or the PET dataset, where the target is encoded as a single integer, is f.nll loss or nn.nll loss. For the version without the initial softmax and f.cross entropy or nn.cross entropy loss for the version with the initial softmax. Since we have a one hot encoded target, we will use BCE with logis loss. Okay, let's do that. Loss func is going to be nn.bce with logis loss. Loss equals loss func active. So we're going to get the results of what we got earlier, compare it with the ground truth, and then let's see what the initial loss is. Ooh. What's going on? Is it because we didn't import Torch? Or let's see. Import what's it? Torch dot what? NN as NN? No. Activations is here. Okay, let's just look it up. What is the error? Type error, loss func, actives, Y. No implementation found for Torch. I'll just type implementation. Okay, let's look that up. So we have this. And let's see here. Maybe it's the same error. Yeah, no implementation found. Cool. Might be another mistake. So we have to convert to a tensor-based object. Is there another way? Ensure that y equals y.float if it's an integer type. Oh, okay, then maybe there is an error right here. Let's see. Yeah, let's just do y.float. So where do we define y to be? Okay. So y equals y.float. Maybe? No. Let's see. I think maybe let's just do it this way. Let's just do tensor base. So on the, I think on the what? Tensor base activations. Let's see what happens. Oh, that kind of looked like it worked. So 1.0467. Okay. Kind of close, right? We don't need to tell fastai to use this loss function, although we can if we want, since it will automatically be chosen for us. Fastai knows that the data loaders has multiple category labels, so it will use nn.bce with logits loss by default. Okay. One change compared to the preceding chapter is the metric we use. Because this is a multi-label problem, we can't use the accuracy function. Why is that? Well, accuracy was comparing our input to our targets like so. So just basically compare the, I guess, the probabilities. Here, the class predicted was one with the highest activation. Okay, activation. This is what argmax does. Here, it doesn't work because we could have more than one prediction on a single image. After applying the sigmoid to our activations, to make them between 0 and 1, we need to decide which are zeros and which are ones by picking a threshold. Each value above the threshold will be considered as a 1, each value lower than the threshold will be considered as 0. So accuracy multi. Okay, let's see if we can just implement that. So we'll have def accuracy multi imp targ thresh 0.5 sigmoid equals true. Sigmoid equals true. So if sigmoid, then we want to calculate the sigmoid of np. Okay, make that space here. Okay, otherwise return np thresh. So if the anything that is greater than, I guess, the threshold in np, check against target booleans, then take the convert to float, then take the mean. Okay, so targ. Cool. Okay, so if we pass accuracy multi directly as a metric, it will use the default value for threshold, which is 0.5. We might want to adjust that default and create a new version of accuracy multi that has a different default. To help with this, there's a function in Python called partial. It allows us to bind a function with some arguments or keyword arguments, making it a new function of that function that whenever it is called, it always includes those arguments. For instance, here's a simple function taking 2 arguments. Okay, so say hello takes 2 arguments, name it and say what. And then it will just return back a concatenated string. Say hello Jeremy, say hello Jeremy ahoy. We can switch to a French version of that function by using partial. Partial is just say hello, say what is bonjour. Then we do Jeremy and Sylvain at the same time. And then, yeah, so bonjour Jeremy, bonjour Sylvain. Okay, so we can now train our model. Let's try setting the accuracy threshold to 0.2 for our metric. Ooh, exciting. Let's do it. So code here is going to be learn equals CNN learner. We're going to pass in our data loaders, resnet 50, ooh, a big one. Metrics is going to be partial, so we're going to bind that function. Accuracy multi with threshold of 0.2. We want to, that's it. Okay, so then learn dot fine tune 3 base LR is 3e negative 3 freeze epochs equals 4. Okay, so it didn't take him too long to train, I guess. For me, it is taking a while, probably a minute or so. So I'll check back. All right, so it looks like we got similar results at the end of it all. About 95% accuracy, validation loss 0.09, and also train loss at 0.09. Cool. Picking a threshold is important. If you pick a threshold that's too low, you'll often be failing to select correctly labeled objects. We can see this by changing our metric and then calling validate, which returns a validation loss and metrics. So let's take a look. Learn.metrics is going to be partial, accuracy multi, threshold is 0.1, learn.validate, and I think things will be less accurate. So if you pick a threshold, okay, so yes, this is going to be, yeah, it just ends up being less accurate. If you pick a threshold that's too high, you'll only be selecting the objects about which the model is very confident in. Okay, so it's about the same. So we can find the best threshold by trying a few levels and seeing what works best. This is much faster if we grab the predictions just once. Let's try that. Okay, so we got something similar. Preds, targs. It's going to be learn.getPreds, get predictions. And then we can call the metric directly. Note that by default, getPreds applies the output activation function, sigmoid in this case for us. So we'll need to tell accuracy multi not to apply it. Okay, let's just wait for this one to finish. Cool. All right. And then accuracy multi preds targs thresh equals 0.9, sigmoid equals false. Okay, about the same. So now we can use this approach to find the best threshold level. Okay, so xs torch.linspace 0.05, 0.95, 29, accuracies, I guess, accuracy multi, preds targs, thresh equals I, sigmoid equals false, for I in XS. Okay, then plt.plot XS accuracies. Looks about the same. So in this case, we're using the validation set to pick a hyperparameter, the threshold, which is the purpose of the validation set. Sometimes students have expressed their concern that we might be overfitting to the validation set, since we're trying lots of values to see which is the best. However, as you see in the plot, changing the threshold in this case results in a smooth curve, so we're clearly not picking an inappropriate outlier. This is a good example of where you have to be careful of the difference between theory, don't try lots of hyperparameter values or you might overfit the validation set, versus practice. If the relationship is smooth, it's fine to do this. This concludes the part of this chapter dedicated to multi-label classification. Next, we'll take a look at a regression problem.